This is the 2015 Level 3 Waves exam, and I'll be working on question 3. Question 3, the whirling buzzer. James attaches the buzzer to the end of a piece of string. James whirls the buzzer around above his head in a horizontal circular radius 1.02 at a constant speed of 16 meters per second. As we can see, this is question 3 of the 2015 exam. It's going to be on the Doppler effect. It's the only one that hasn't been covered so far. Question A, describe the motion of the buzzer when Sabina receives sound waves with the shortest wavelength. So instead of having the buzzer going around his head like that, it's probably easier to have it like this here. And I know from over the page the velocities. If it's going this way, here we go, going that way. That's the direction of the buzzer going around and around. When the shortest wavelength occurs, so I'll just put shortest wavelength occurs when the buzzer is here we go. So I've said the shortest wavelength occurs when the buzzer is moving directly towards her. The reason for that is when the buzzer is moving directly towards her, the waves bunch together. Because the velocity stays constant, when the waves bunch together, we get a higher frequency, and that is the Doppler effect. Right? If the frequency emitted by the buzzer is 512, show that the lowest frequency heard by Sabina is 489. So here we use the Doppler formula, which is F dash, so the observed frequency is equal to F velocity of the wave. This is times here divided by velocity of wave plus or minus the velocity of the source. In this case, it must be going away from her because the buzzer must be going away because she's hearing 489. So in order for this observed frequency to be less than this observed frequency, this number here, this number here needs to be less than 1. And in order for this to be less than 1, the denominator needs to be larger than the numerator. So in other words, it just means we cancel out this minus, so it's a plus. So we have 5, which equals 512 hertz, times 343 divided by 343 plus 16, because the buzzer is moving at 16 meters per second, and that does indeed equal 489 hertz. And just another thing, all numbers have given us in 3SF, everything's in 3SF, so our answer needs to be in 3SF, which it is. Cool. Question C. Sabina stands a very long way from, she stands away from James, listens to the buzzer. The sound appears to be increasing in frequency as the buzzer travels from point C to point A. Explain why Sabina hears an increased frequency between points C and A. You may want to use calculations in your answer, which means we have to use calculations in our answer in order to get full marks. So let's just draw some velocity vectors here. So we got, there we go, and here we go. So I'm going to answer this two ways. First, I'm going to answer with the diagram. So we got V here. So I'm just put moving towards what's her name, Sabina, and if it's moving towards Sabina, that's the highest frequency that's going to be heard because wavelengths are going to bunch together, the velocity is constant, and I'll just put V equals F lambda up here. If our wavelength decreases, our frequency increases in order to keep the velocity constant, which it is. Moving towards Sabina, highest frequency, put F, and I just put in brackets because we need to calculate this. We've calculated the lowest frequency, we did it on the page, but we'll calculate the highest frequency. F dash equals F times VW, is the velocity of the wave, over VW, and because this is going to be higher, our denominator needs to be less than the numerator, so that means we have to minus velocity of the source, and I'm not going to put the numbers in, I'm just going to tell you now, it's 537, if you calculate that out, it's 537 hertz. So, and let's put this highest 537 hertz, here we go. That's moving towards, over at D we have no velocity in Sabina's direction. Thus actual, well, this should be emitted, actually, emitted if heard. That's 512. And at C, moving away, Sabine is lowest F, which is 489. You calculate that over the page. In fact, we were given that, and I need to put hertz in here as well. Right. So this would actually be enough. I've used diagrams, I've used calculations, but I'm also going to just give a brief explanation as well. At point C, right, so what I've written here, I'll fast forward my writing. So at point C, the buzzer is moving directly away from Sabina, so she'll hear the lowest frequency, 489. At point D, the relative velocity between the buzzer and Sabina is 0, so the actual frequency, 512, will be heard. And as you can guess it, at point A, right, so I've said, we see that. So I'll just go through the whole thing. So at point C, the buzzer is moving directly away from Sabina, so she'll hear the lowest frequency, 489 hertz here. At point D, the relative velocity between the buzzer and Sabina is 0, so the actual frequency, 512, will be heard. At point A, the buzzer is moving towards Sabina, so the highest frequency, 537, will be heard. There's another little thing we could say is from C to A, C to A, the frequency will be increasing as the relative velocity changes. Right, last question. James wants Sabina to hear beats He puts a second buzzer, which is also emitting a sound of 512 on the ground. James again whirls the original buzzer over his head, but at a different speed. When the buzzer is at point A, so here, where is it here? He lets go of it. The buzzer off flies towards Sabina. Sabina hears 10 hertz beat as James releases the string. Calculate the velocity of the buzzer at the point of release. Right, so we've got to start off with the beat frequency first. With F beat, because we want to work out the frequency of the buzzer when it left its hand equals magnitude of F1 minus F2. So this is the beat formula, but you really need just to know that beats are just the difference between the two, or the beat frequency is a difference between the two frequencies. I know for a fact that because the buzzer's whizzing towards Sabina, it's going to get Doppler shifted. It's going to be a higher frequency because it's moving towards Sabina because the wavelength is going to be shorter. In other words, the buzzer moving towards Sabina is going to be at above 512, and because it's a beat frequency of 10, it's going to be 10 hertz above 512 because the beat frequency is just the difference between the two frequencies. So I can go ahead and I can write F2 as the frequency of the buzzer moving towards Sabina is equal to magnitude of F beat plus F1, which is equal to 522 hertz. But for this here, you just need to think about it in terms of what actually happens. You sort of need to know the answer before you have a go at working it out through intuition. Right, F dash is equal to 522. Good, that's in 3SF as well, per hertz. F dash is equal to frequency times VW over VW minus VS. Have I written that? Yep. So this is just rearranging. I want to rearrange for the velocity of the source. There are many ways you can rearrange for that. It's no real particular order, but I'll just move the original frequency to the other side. So I'm going to divide both by F. F dash equals V wave source divided by velocity of the wave. And because, one thing I didn't mention, because it's got a higher frequency, it needs to be a minus, because this here needs to be bigger than 1 to make our actual observed frequency larger than the emitted frequency. Cool. So we will times both sides by this here. We're going to times both sides by this here. Sorry if my video is lagging a bit. So V wave source minus VS equals, and I'm going to move the F and F dash to the other side at the same time, so they'll just be flipped upside down. So I'm going to get F divided by F dash times V wave source, and then all I need to do is move my wave source to the other side. So I'm going to get minus VS equals F over F dash times V wave minus V, the wave speed. And if you plug this all in, you should get minus 6.57 meters per second minus 1, and well, it should be positive actually. V source is actually positive because there's a negative here, so it should have given you a negative number, but because V source is actually negative, we get positive 6.57 meters per second. And noticing it's got to be in 3SF. Yeah, and we'll just double check we answered that. So we know the buzzer is going to have, you know, a decent velocity. 6.57 is reasonable. Just double checking. Yeah, emitted frequency was larger than the Doppler shift frequency is larger than the emitted, and I think that's about it.